I have a chair in my shop that was built sometime around 1840. It belonged to my wife's great-great-grandmother, and it came out of a cabin in the Blue Ridge Mountains of North Carolina. The seat is solid poplar, the legs are hickory, and every joint is a hand-cut mortise and tenon wedged from the outside. That chair has survived 180 years, 2 house fires, 4 generations of children, and it still does not wobble. Last winter, my daughter bought a kitchen table from one of those big Scandinavian furniture stores. Nice-looking thing. Came in 2 flat boxes. 6 months later, the legs were loose, the top was sagging in the middle, and the whole thing racked sideways if you leaned on it while cutting a steak. She paid $300 for it, and it did not last through a single football season. That got me thinking about what exactly is different between these 2 pieces of furniture. Not just the obvious stuff, not just real wood versus fake wood, but the actual physics of why one holds together for centuries and the other starts failing before you finish paying off the credit card. Today, I am going to walk you through exactly what traditional mountain furniture makers understood about wood, joinery, and forces that modern factory furniture completely ignores. And stick around to the end, because I have a trick for testing joint strength before you even glue anything up that I learned from studying these old chairs. Let us get into it. The furniture that came out of the Appalachian Mountains from roughly the mid-1700s through the late 1800s represents some of the most honest, durable woodworking ever produced in North America. And I want to be clear about who made it. These were not wealthy cabinet makers with fancy shops. These were Scotch-Irish and German settlers who came into the mountains with almost nothing. They had hand tools, they had the timber growing on their land, and they had a very practical problem. They needed furniture that would survive hard daily use in rough conditions, and they could not exactly run to town and buy a replacement when something broke. What they developed over generations was a system of building that worked with the wood rather than against it. They understood things about grain direction, seasonal movement, and mechanical advantage that honestly put a lot of modern engineering to shame. And they learned it not from books, but from watching what failed and what lasted. The guiding principle was simple. Build it once. Build it so your grandchildren never have to build it again. Every decision they made, from which tree they cut to which direction they oriented the grain in a joint, served that principle. And when you start examining their work closely, you realize there is real science behind every choice, even if they never would have called it that. So let me show you what they did and why the physics actually works. The first thing traditional mountain furniture makers did that almost nobody does today is match the grain direction at every joint. When I first heard the term grain matching, I assumed it was about appearance, about making the wood look nice. It is not. It is structural engineering. Here's what I mean. Wood is not equally strong in all directions. Along the grain, a piece of white oak can handle over 7,000 pounds per square inch in compression. Across the grain, that same piece might fail at 1,000 pounds per square inch. That is a 7-to-1 difference. Mountain builders understood this intuitively. When they joined a chair leg to a seat, they oriented the grain in the tenon so that the primary stress, the downward compression of someone sitting in the chair, ran along the strongest axis of the wood. And they made sure the mortise in the seat was oriented, so the grain of the seat supported the tenon against the most likely direction of force. This is the opposite of what happens in factory furniture. In a flat-pack chair, the leg typically connects with a short dowel or a metal camlock, and nobody is thinking about grain direction at all. The particle board has no consistent grain. The dowel is often cross-grained to the stress. The result is a joint that is fighting the physics from the moment you assemble it. Now let me get specific about the joints themselves, because this is where the difference becomes dramatic. A traditional mountain chair leg connects to the seat with a through mortise and tenon. The tenon on a typical chair leg might be 1 inch wide, 3/4 of an inch thick, and it passes completely through the seat, sometimes protruding a 1/4 inch on the other side where it gets wedged. That joint has a glue surface area of roughly 6 square inches, and once the wedge is driven, it creates a mechanical lock that actually cannot pull apart without destroying the wood itself. Now compare that to a modern flat-pack connection. The most common joint in flat-pack furniture is a cam lock and dowel system. You have a short pine or birch dowel, usually about 1 3/8 inches long and a 1/4 inch in diameter. That dowel sits in a hole drilled into medium-density fiberboard or particle board, and a zinc cam lock twists to grab it. The total effective glue surface is less than 1 square inch, and more importantly, the cam lock is relying entirely on the internal bond strength of the particle board to hold. Particle board has an internal bond strength of roughly 40 to 80 pounds per square inch. White oak has a shear strength along the grain of over 1,000 pounds per square inch. You are comparing a joint that can resist hundreds of pounds of racking force to one that starts to crumble at 40. By the way, if you are enjoying learning about these old-world methods, I put together something I think you will really appreciate. It is called The Old Ways, and it is a collection of 100 forgotten woodworking secrets from traditional craftsmen around the world. Techniques like the ones we are covering today, and a whole lot more. You can grab your copy by scanning the QR code on screen, or just use the first link in the description. All right, let us keep going. Now here is where the physics get really interesting, and this is the part that made me completely rethink how I look at furniture. The force that destroys most furniture is not compression. It is not someone sitting on it. It is racking. Racking is a lateral force, a sideways push that tries to turn a rectangle into a parallelogram. Every time you scoot a chair back from the table, every time you lean sideways, every time a child tilts back on 2 legs, you are introducing racking force. A properly made mortise and tenon joint resists racking because the tenon has shoulders. Those shoulders, the flat faces where the rail meets the leg, create a broad bearing surface that physically prevents the joint from rotating. On a traditional mountain chair with a 1-inch tenon passing through a 2-inch thick seat, you have a shoulder bearing against nearly 2 full inches of solid hardwood. The joint simply cannot pivot. The geometry will not allow it. In a flat-pack joint, there are no shoulders. The cam lock and dowel system has 0 resistance to rotation except friction and the compressive grip of the cam itself. The moment that grip loosens even slightly, and it always does because particle board compresses and deforms under sustained load, the joint begins to rack. Once it starts racking, the hole elongates, the cam loses even more grip, and you are in a death spiral of progressive loosening. This is not a defect. This is physics. The joint was never designed to resist racking in the first place. The fourth thing mountain builders understood was wood selection, and I do not just mean picking a pretty board. They selected specific species for specific structural roles, and they harvested with the seasons. Chair legs were almost always made from hickory or white oak, the 2 strongest domestic hardwoods available in the Appalachian forest. Hickory has a modulus of rupture over 20,000 pounds per square inch, meaning it can flex significantly before it breaks. That is why it was also used for axe handles and wagon spokes. It absorbs shock. Seats were often poplar or white pine, softer woods that were easy to carve and shape, but still dimensionally stable. And here is the part most people miss. They cut their timber in late fall or winter when the sap was down. A tree cut in January might have a moisture content of 35%. The same tree cut in June could be 50% or higher. Lower initial moisture means less shrinkage as the wood dries, which means tighter joints that stay tight. Compare that to flat-pack furniture, where the primary material is medium-density fiberboard made from wood fibers and resin pressed under heat. MDF has no grain, direction, which sounds like an advantage until you realize it also has no natural resistance to splitting, no flexibility, and it absorbs moisture like a sponge. One spill on an MDF tabletop, and the surface swells permanently. Once I saw how they handled joint geometry, the next thing I noticed was how mountain builders used wedged-through tenons to create what is, essentially, a permanent mechanical lock. This is elegant in its simplicity. You cut the tenon slightly narrower than the mortise at the top, then you saw a kerf down the center of the tenon before assembly. After the tenon passes through the mortise, you drive a small hardwood wedge, usually white oak or hickory, into that kerf. The wedge forces the tenon to expand inside the mortise, creating a dovetail-like flare that physically cannot be pulled back through the hole. The beauty of this joint is that it actually gets tighter with age. As the wood dries and the fibers compress around the wedge, the mechanical lock increases. I have disassembled old mountain chairs where I literally had to drill out the wedge and drive the tenon back through with a mallet and a steel rod because the joint had become essentially monolithic. Try that with a cam lock and a particle board panel, and you will just end up with a pile of sawdust. This leads directly to the most fundamental difference in design philosophy between these two traditions. Mountain furniture was designed to be repaired. Flat-pack furniture is designed to be replaced. A mountain chair with a broken spindle could be taken apart, the spindle re-drilled and replaced, and the chair reassembled with new wedges. The joints allowed for disassembly because the wedges could be drilled out. The wood was solid enough to accept new joinery. The whole system assumed that individual parts might fail over a lifetime, but the overall piece would endure. Factory furniture cannot be repaired because the materials cannot accept rework. You cannot recut a mortise in particle board. You cannot re-wedge a joint in MDF. Once the fibers around a cam lock hole have compressed, that hole is permanently wallowed out. The manufacturer knows this. The furniture is priced to be disposable. That $300 table my daughter bought was never intended to last more than 3 to 5 years. It is a consumable product, not a durable good. Let me share some patterns I have noticed over the years, things I used to do myself that this tradition handles completely differently. The first pattern is trusting the fastener instead of the joint geometry. Most of us reach for screws or dowels and assume the fastener will do the work. Mountain builders trusted the shape of the joint itself. The fastener, the wedge, was just insurance. The second pattern is ignoring grain direction when orienting joints. I did this for years because I was thinking about appearance, not about which way the load would travel through the fibers. Once I started orienting my tenon so the grain ran parallel to the primary stress, my joints got dramatically stronger with zero extra effort. The third pattern is building with materials that cannot be reworked. Every time I used MDF, or particle board in a structural roll, I was building something that could never be tightened, never be repaired, never be improved. That is a dead end. The fourth pattern is designing for assembly speed instead of long-term stability. Flat-pack furniture exists because it is fast to assemble. Mountain furniture exists because it is slow to fail. Those are opposite goals, and the results are exactly what you would expect. The good news is, once you see these patterns for what they are, you can start shifting your approach, one project at a time. Now, for that bonus tip I promised at the beginning, this is something I figured out from studying old mountain chairs, and it has saved me more than once. Before you glue up any mortise and tenon joint, dry fit it and then try to rack it by hand. Grab the rail and push it sideways, hard, while holding the leg steady. If the joint moves at all, even a little, your shoulders are not tight. A properly fitted mortise and tenon with good shoulders should feel absolutely dead when you try to rack it. No movement, no flex, no play. If you feel any give, take the joint apart, check your shoulder fit with a straight edge, and pare until it seats perfectly. This 5-second test tells you more about the long-term durability of your joint than any amount of clamping pressure or glue will ever fix. I started doing this on every joint about 3 years ago, and I have not had a single piece develop a wobble since. It is the simplest quality check in woodworking, and I have never seen it mentioned in a single modern how-to book. Before you head out, I want to make sure you know about my book, The Old Ways. It goes way deeper than any single video can, with 100 forgotten woodworking techniques from traditional craftsmen, 75 detailed photos, and 122 pages of real hands-on knowledge. If you want to bring these old-world methods into your own shop, this is the guide to do it. Just scan the QR code on screen or click the link in the description to get your copy. Thanks for spending time with me today. And if you have not already, hit that subscribe button so you do not miss the next one. I will see you in the next video. Until then, build it like your grandkids are going to use it.